All right, this is going to be the lecture over chapter 18. We're going to be discussing temperature, heat, and the first law of thermodynamics. Okay. Thermodynamics is the study and application of the thermal energy of systems. Often it's called internal energy. One of the central concepts of thermodynamics is temperature. Temperature is an SI-based quantity related to our sense of hot and cold. It is measured with a thermometer, which contains a working substance with measurable properties such as length or pressure that changes in a regular way as the substance becomes hotter or colder. That way we have a way to gauge it. Physicists measure temperature on the Kelvin scale, which is marked in units called kelvins. Over on the right, you can kind of see temperature. This is very, very cold up to a very, very hot, and a lot of distance in between. So you can kind of see the markings there as far as where you see what. Kelvin has a very interesting property in that it doesn't have negative values. Once you hit 0 Kelvin, that is absolute zero. You're not going any lower than that. The same cannot be said of Celsius or Fahrenheit. And so this is one reason why it's used in scientific studies. Two bodies are in thermal equilibrium if they are at the same temperature throughout, and therefore no heat will flow from one body to the other. This is often referred to as the zeroth law of thermodynamics. And the reason is that they had already developed your first and second laws, but this is more fundamental in the sense that if you have two different bodies that are in thermal equilibrium with a third, then they have to be in thermal equilibrium with each other. It doesn't sound very intricate. It doesn't sound very involved, but it's a very important property in that we have to have some way to be able to gauge whether or not something has heat flow from it or not. And this is one standard that we keep in regards to that. And it's fundamental enough that they go ahead and list it as the zeroth law rather than the first. Triple point of water. The triple point of water is the point in which solid ice, liquid water, and water vapor coexist in thermal equilibrium. Obviously, this does not occur at normal atmospheric pressure. By international agreement, the temperature of this mixture has been defined to be 273.16 Kelvin. The bulb of a constant volume gas thermometer is shown inserted into the well of the cell. So you've got the cell down here, you've got your thermometer bulb, you've got ice that is existing around this side, you've got vapor over here, and then you've got water, all three of these existing at the same time. So that's why they call it the triple point, as all three phases exist at the same time. A constant volume gas thermometer. It consists of a gas-filled bulb connected by a tube to a mercury manometer. By raising and lowering the reservoir R, the mercury level in the left arm of the tube can always be brought to the zero of the scale to keep the gas volume constant. So this is your scale. As you take or give into the reservoir, you can adjust the volume of the gas over here. The recipe for measuring a temperature with a gas thermometer, where P is the observed pressure and P sub 3 is the pressure at the triple point of water, is going to be listed as this: 273.16 Kelvin times the limit as gas approaches zero of P divided by the pressure at the triple point. Okay, Celsius temperature scale is defined as your temperature in Celsius is equal to the temperature in kelvins minus 273.15. So there's a scaling factor involved there. The Fahrenheit temperature scale is defined as temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. So that is how indeed you convert from one to the other. And then if you really wanted to, you could take this one, substitute it in here, and figure out how to convert Fahrenheit to Kelvin. So here are some values of temperatures and their degrees in Celsius and degrees in Fahrenheit. A lot of these you may have come to know. Some of them you may not have. You can see here at absolute zero, these are what all of these values are. And then the triple point of water, which happens to be here, that's what the values are here in the corresponding scales. All right, linear expansion. All objects change size with changes in temperature. For a temperature change of delta T, a change delta L in any linear dimension L is going to be given as the following. One other way to look at this particular equation is to take delta L divided by delta T. And so you've got a coefficient of linear expansion, alpha, multiplied by the length. So the change in L divided by the change in temperature will be some coefficient multiplied by the length. And different amounts of expansion or contracting can produce bending. As a matter of fact, this particular type of thermocouple is what you're going to see in a lot of the older thermostats in houses. If one expands in one direction or the other, basically it's going to make contact and create a current, which is going to tell the system to kick on, the air conditioning system or the heater to kick on or to turn off. Because different amounts of expansion or contraction will produce a bend. Volume expansion. If the temperature of a solid or liquid whose volume is V is increased by an amount delta T, then the increase in the volume is found with this equation. Again, if you take both sides and divide it by delta T, basically what you're saying here is the change in volume with respect to whatever your change in temperature is going to be some constant coefficient multiplied by the volume you already had. Now, beta, your coefficient of volume expansion, is going to be related to the coefficient of linear expansion by the factor of 3, which is a little convenient. Okay, so checkpoint 2. You've got a figure here that shows 4 rectangular metal plates with sides of L, 2L, or 3L. They're all made of the same material, and their temperature is to be increased by the same amount. So rank the plates according to the expected increase in their vertical heights and then their areas. And start with the greatest and then work back. So if you look at the vertical heights here, the vertical heights here are going to be the same. Now remember, their vertical height change is going to be a function of the change in temperature. The temperature is to be increased by the same amount for all of them, but that change is going to be greater if the length is greater. And if they're all made of the same substance, This value is going to stay the same. So this value and this value are the same. The only thing that's going to change is the L. And since these two are taller than the other two, that's why 2 and 3 are listed. Don't pay any attention to that minus sign out there in the front. 2 and 3 are going to be changing the largest amount, followed by the next highest, and then followed by the shortest. Now, if we look at the areas, then we're going to be looking at this with the greatest area. This will be the next greatest area, and then 1 and 4, which have equivalent areas, are going to increase the least amount. Okay, temperature and heat. Q is going to be the letter that's used to represent heat. And heat is going to be the energy that is transferred between a system and its environment because of a temperature difference between them. It can be measured in joules, it can be measured in calories, kilocalories, or British thermal units, just whatever floats your boat at the time. And then you can see the conversions down here. 1 calorie is equal to this number of BTUs, which is equal to this number of joules. So if we zoom in here, we have a system here which has a certain temperature. That's why it's T sub S. And then the environment in which you find it is going to have a temperature T sub E. In this particular case, the system has a higher temperature. So what you're going to see is you're going to see a flow of heat from the system into the environment. So it's going to lose its energy as heat. Now, that's probably not too much of a surprise. If the temperature and of the system and the environment are the same, you're not going to have any transfer of heat. If, however, the temperature of the system is less than the temperature of the environment, you're going to have an inflow of heat into the system. So Q is going to be greater than 0. Q, you are looking at what the system is gaining or losing. And that's an important perspective to keep in this particular discussion. So absorption of heat by solids and liquids. The heat capacity of an object, and that's going to be represented with capital C. The heat capacity of an object is the proportionality constant between the heat that the object absorbs or loses and the resulting temperature change of the object. So this is the amount of heat gained or lost. This is going to be the change in temperature. If you divide both sides here by delta T, then the heat over the change in temperature is going to be your heat capacity. Obviously, the more heat that you can contain, the greater your heat capacity. You can also write the change in temperature in this, where the final temperature minus the initial temperature will get you the change. If the volume has a mass m, then Q is going to be equal to Cm delta T. And the small c is going to be the specific heat of the material making up the object. So, checkpoint 3. A certain amount of heat, Q, will warm 1 gram of material A by 3 degrees Celsius and 1 gram of material B by 4 degrees Celsius. Which material has the greater specific heat? Well, specific heat, we're going to use this particular formula. We're using the same amount of heat for each type of material. So Q is always going to be the same. It's going to be the same in both cases. 1 gram is going to be heated of each material. Therefore, M is going to be the same. Now, what we're seeing here is that amount of heat is being applied to material A, and it's going to warm it by 3 degrees. For material B, it's going to be warmed by 4 degrees. So if we go here, our change in temperature for material A is going to end up being 3 degrees. So if you take whatever that amount of Q is, M, we're just going to pretend is going to be 1. This is going to be 3. So we're going to have Q divided by 3. So that's going to be the specific heat for material A. Now, if we go to material B, it's going to be heated by 4 degrees. So if we take Q and divide it by 4, that's going to be the specific heat of material B. Now, if you take something and you divide it by 3, that's going to be greater than if you take something and you divide it by 4. That's why material A is going to have the greater specific heat. Okay. So when quantities are expressed in moles, specific heats must also involve moles rather than mass unit. Then they are then called molar specific heats. And the table will show the values for some elemental solids, each consisting of a single element at room temperature. The amount of energy per unit mass that must be transferred as heat when the sample completely undergoes a phase change. In other words, if it goes from solid to liquid or liquid to gas or the other way around, that's going to be called the heat of transformation. That's going to be denoted with the capital letter L. Thus, when a sample of mass M completely undergoes a phase change, the total energy transfer is going to be the heat of transformation multiplied by the mass. So you've got specific heats here for elemental solids, expressed in different units. So sometimes those values will come in handy with problems. Okay, heat and work. A gas may exchange energy with its surroundings through work. The amount of work done by a gas as it expands or contracts from an initial volume to a final volume is going to be given by this. In other words, we're going to take the same type of definition that we have for work, force times distance, and we're going to apply it in this particular case. In this particular case, it's going to be pressure times the volume, the infinitesimal volume. And we're going to integrate that from some initial volume to some final volume. So the integration is going to be necessary because the pressure may vary during the volume change. In other words, it's going to be a function of, it could be a function of volume as well. So we're going to need to be able to integrate that. And we can't just call it a constant. In some cases, we might be able to, but it depends on the circumstance. So, for instance, here, let's kind of go in here. We've got a thermal reservoir. We've got our insulation. We've got some lead shot here that is weighing on this piston. And we've got a temperature here. So if we adjust the temperature, if we turn the temperature up, we're giving the molecules in here more energy, and that can work to raise this lead shot. That is considered to be doing work. All right. So let's take a look at a few examples here. We've got a gas that moves from some initial volume to some final volume. And if it does positive work, the work that is going to be done is going to be the pressure multiplied by the volume. In other words, it's going to be the area under this particular curve. It is also going to be considered to be, the work is going to be considered to be greater than 0. We'll get into that here in a little bit. If we look at part B, we can still see that it goes from I to F, but it does more work because it moves at a constant pressure out to this particular volume, and then it goes down to this spot. So we can see that the work here is greater than 0, but it's greater than what we were doing over here. If, however, the pressure were to drop initially, but no volume change, and then the volume changes with constant pressure, that has less work than what we see over here. So depending on the area under this particular path that is taken will tell you how much work is done. If you look at this area, and this area, you can compare those. Now, we can control how much work is going to be done depending on what sort of path we wish to take. If we are to move from F to I, we are considering that the system has done negative work. You can't say that work is not being done by the system, but perhaps on the system. And then cycling clockwise yields positive net work. And the reason is that you do a certain amount of work in going from this direction, which is considered to be positive, but as it moves back like this, that is going to be negative work. When you take the difference between this and what you see over here, this is the volume that you get. First law of thermodynamics. The principle of conservation of energy for a thermodynamic process is expressed in the first law of thermodynamics, which may assume either of these two forms, either the internal energy, which is going to the change in the internal energy, which is the energy that you have internally at the end minus the energy that you had internally at the beginning, is going to be equal to the heat minus the work. That's going to be the first law. Or if the system, if the thermodynamic system undergoes only a differential change, we can write it such as this, if we're looking at something that may be more continuous. So the internal energy of a system tends to increase if energy is added as heat, and tends to decrease if energy is lost as work is done by the system. In other words, the more work the system does, then the internal energy tends to decrease. If you add in more heat, then the internal energy of the system is going to increase. Seems kind of obvious when you look at the formula there, but all right. So we have four special cases here. And again, this is the first law of thermodynamics. We have a process here. We'll go through all four of these. The first process here is considered adiabatic. And what that means is it's a fancy word saying that there is no heat exchange between the system and an environment. So Q is equal to 0. There's no exchange. So what does that mean? That means that any change in the internal energy is going to be the negative of the work that's done by the system. If we look at a constant volume, the volume doesn't change. If you'll remember, if we go back and look at this, if we were to integrate from VI up to VI and it doesn't change, work is going to be equal to nothing. So if work is equal to nothing, then that means the change in the internal energy is going to be just Q. If we were looking at a closed cycle, in other words, we follow the same path backwards and forwards, there is no exchange in the internal energy, and so that the energy is going to, the heat is going to be equal to the work. Free expansion means that heat is not added to the system, work is not being done by the system, so that means the change in internal energy of the system is going to be 0. Thermal conduction. The rate at which energy is conducted through a slab for which one face is maintained at a higher temperature and the other face is maintained at a lower temperature is going to be referred to as this. it's going to be Q divided by T, which you can also say is going to be the thermal conductivity of the material times the area A of each face of the slab, and then the difference here in between the two, and then the distance between the two faces. So we've got a steady transfer of heat. We've got a hot reservoir here. We've got our surface here. It has a thermal conductivity here. And then, as you would expect, the heat runs from the hot to the cold. So energy is transferred as heat from a reservoir at temperature TH to a cooler reservoir at TC through a conducting slab of thickness L and thermal conductivity K. Convection. Convection occurs when temperature differences cause an energy transfer by motion within a fluid. When you look at a flame of a candle or a match, you are watching thermal energy being transported upward by convection. Convection is part of many natural processes. Atmospheric convection plays a fundamental role in determining global climate patterns and daily weather variations. And glider pilots and birds alike seek rising thermals, convection currents of warm air that keep them aloft. Huge energy transfers take place within the oceans by the same process. Thermal radiation. Radiation is an energy transfer via the emission of electromagnetic energy. The rate at which an object emits energy via thermal radiation is going to be given with this particular formula. You can see that it depends on temperature to the fourth power. You've got the Stefan Boltzmann constant, that's going to be sigma. You've got the emissivity of the object's surface. A is going to be its surface area, and T is the temperature in kelvins. And the absolute rate at which the object absorbs energy via thermal radiation from its environment, which is a uniform temperature, is going to be given as follows. Okay, so that's your introduction to thermodynamics. A lot of these make sure to go over in the text and work as many problems as you can. That will help you understand the subject a lot better.